Good day, gentle general readers and curious fellow earthlings. Welcome to another Logos 2000 from a desk with Ross Finlayson here in Seattle, Washington, January 4, 2024. The previous installment was about time series and the sampling, measurement, and observer effects with regards to precision and accuracy, and then as with regards to numerical methods and the ideas of the practice of sampling, observation, and measurement, and how those are always involved in this system that they so sample, observe, and measure. And then as with regards to sampling and events, these concepts of the elementary objects from statistics and probability theory, how samples and events are variously considered as with regards to the probability distributions of events, and then as with regards to the samples they're gathering, and then as with regards to samples and events and samples, that is just kind of considered that's part of then the phenomenological account as with regards to why then that's usually considered part of science and what's reproducible and observable and measurable. And then as with regards to theory and it being falsifiable, whether it validates or not the theory, and rather that it invalidates or not the theory. And it's similar with the statistical hypothesis. There's no saying that something, according to science and the statistical method, is so. It's just not so according to the theory. And so there are any number of theories, of course, and any number of statistical hypotheses, and then that's all considered to be good science, and according to the philosophy of science, according to the reason why it is so. And here for this stronger logicist positivism of scientism, in this universe of this stronger mathematical Platonism, the real true objects of mathematics and the theory. So then about the consideration of the course of numerical methods and why the numerical methods are either closed forms and they include or not other algebraic quantities of numerical methods, or perfect numbers, plain numbers, pure numbers, or that as numerical methods, when not closed forms, they're but approximations, and they always have a formal error term, that the approximation has got two components, a of x and e of x, which is the approximation and the error term. That then the modeling the bounds of the error terms is the most usual idea in numerical methods, to arrive at then being able to say that a given approximation holds good and doesn't explode, is the usual idea when it does not hold good. And so then with that being kind of the course of the previous episode, I don't really have too much more to add to that, except that that's always kind of inherent in everything with regards to that being the work in theory, even if unconsciously, for all such matters of the deliberation and contemplation as with regard to data. The word data or data, it's usually pronounced data, and it's a plural. It's kind of like with samples and events. They're always kind of like sample and events always includes, for example, time series associated with it. So data is plural, and a datum is a particular piece of data. And so a data and the datum, then the most usual associated term these days is big data or data science. The idea that according to the embarrassment of computing resources afforded by after Moore's law and many decades of the development of the economy of machinery that makes computations and stores data, gathers, collects, and stores data, and communicates data. With regards to something like signal theory, information and signal theory being the kind of the fundamental theory of what that is with regards to the transmission of signals and data, And then that big data is the idea is like, well, now it's tractable to deal with billions and billions and billions of data points with regards to what before would be just kind of aggregates and the averages. As with regards to in the deterministic data, there's like counting every penny, and then in the indeterminate, non-deterministic data are estimates, and summary statistics that are memoryless, like averages in what, or get with absent counts, or otherwise with regards to statistics and summary statistics, the analytic and aggregate functions that result over a corpus or a body of data, that a corpus is a body, and corpi or corpuses are plural of a corpus, that are given a body of data, then all these different algorithms can be made on the data that in the theory of the database, that the database is usually with regards to the theory of relational algebra. So it's like, what's in a database? Well, it's data of particular kinds or types, and so they're called relations, but it means usually when people say that, they think tables. And so a table is a relation of given columns, then that points within those are also relations. It's all relational algebra. Or here has been considered that a relational database management system is according to relational algebra, except with rows and nulls, because in a plain pure relational algebra of a simpler kind, there's not really an idea of a row, and there's not really an idea of null, which is the absence of data. Yet usually it's just considered to take the Cartesian product of relations, and when they're not fulfilled, then those are nulls, and then the whole outside coordinate of that is the rows. So the database then is just the idea of kind of like the notion of the basis or the bases of a coordinate space, has that the database then is also just considered as like that's where all the data lives, is inside the database. The database is then one of these four fundamental sort of facilities in computing and distributed algorithms: the database, the file system, the message queue, and the web services. That's kind of how I categorize everything in terms of algorithms and distributed information systems as regards to data processing. So then big data is just data when it's big. And then there's some ideas that given all these kinds of algorithms, that more and more kinds of relations can be discovered in the data, or according to statistical hypotheses and then a kind of more thorough and conscientious and critical account, they can have established statistical hypotheses that via statistical inference aren't invalidated. And so then data science is just kind of this idea of various aggregate and analytic algorithms, where an aggregate algorithm is to take like a sum or a total or a count, and then mean, median, and mode are kind of considered as that aggregates, although they kind of enter the analytic, because the analytic and data just means, in the theory of databases and in all databases, they're called aggregate and analytic functions, which then makes for collecting by groups and then computing subtotals of those. And then there's also what are called hierarchical functions, that basically in all sorts of databases, there's queries, it's usually called select, that among the various commands of the data modification language are insert, update, and delete. And then in the data definition language is as with regards to create, alter, and drop. And then as with regards to select, the other command, that select is most people's most usual idea of a query of the database. And then it has a column list, and it selects from a table-like expression, and that every one of these has a particular syntax according to the language called SQL, SQL, or SQL. And that then there's with common table expressions and these kinds of things, making names for queries, and then each of those is like a table-like expression that from you select a column list from a table-like expression where adding conditions that something is so according to expressions on the columns and any kind of functions on these IDs of the data. And then to group these things, and then have for these groups when they're having something, and then to order these things that any one of these queries is select from where having order by, or select where from where group by having an order by. That this is just the way that it is for all these things. And then it has this set associative. That the relational database is, according to relational algebra, that it's all set associative. And so then what results is after the column list, and according to the names and correlative names, then there's what results tuples, which are kind of like vectors. They just have like element A, element B, element C, or here column 1, 2, 3, the columns. The values in each of these columns, the tuples, that it results a set of tuples, the usual idea of what's data, and this kind of idea. So then if that's about data, so there's big data and then data science and then the database. And so these are just dealing with the information. So information theory and signal theory are these particular branches of analysis, and what they're associated with include things like transmission of communications and telecommunications. And so that's all signal theory. And within that is kind of defined by information theory. So signal theory is kind of like the continuous aspect of that. And signals usually considered as like waves. And then information theory then gets kind of into the binary. And there, yet it's not exactly that, so it's a bit fuzzy about that. But the signal and information theories then basically define notions like bandwidth, and so when learning about something like the invention of television and the old-fashioned over-the-air television, analog television, and as with regards to bandwidth and 6 megahertz range of this, and what are channels? The channels are according to this bandwidth, according to this frequency modulation and the range. And then those represent a waveform. That a waveform is, it's like a wave, but then how it's considered is that it's a line of waves. And so something like waveform audio has that for given particular frequencies that are sampled, these are the samplings of the frequencies, then each one of those is quantized, and then it results that as it increases and decreases in amplitude, then that's the waveform. And then the wavefront is a given particular sample at any given instant. And so these samples are a usual given number of times per second, cycles per second, or hertz. It's a unit for 1/2. That so many of these then helps define like that megahertz means millions per second. And otherwise the idea of waveform audio, and then getting into notions like A law and mu law, these sampling approaches to waveform audio, have that these are then the way that there's what's called analog to digital conversion and digital to analog conversion. So the ADC or the DAC is an analog digital converter, or the digital and analog converter. And the idea is that a given signal in the digital form is a waveform, and as with regards to then that is a waveform representation of the analog data, the audio, or is with regards to video, that video is usually kind of just like, well, it's like a billion different eyes, so each pixel is a different one, and then that just is used to make a most usually pixels, picture elements, and then that those are sampled by analog to digital conversion, as with regards to then converting them in the color space in usual color television, usual video, say, the digital variety, and with that being basically what's called, could be called raw, then that's converted into various digital encoding formats that then via various mathematical methods of analysis, like the transforms, then it could result that the continuous tone of the imagery is what can be made into that for the entire frame. That a given frame is it has that motion picture video is something like 30 frames per second or 60 frames per second. That's considered quite high resolution of the things. That resolution and accuracy and precision are related terms. Then that this signal and information theory defines what is this data that's audio or video. And then how it arrives into the digital is with the loss of these things. In the conversion of analog to digital, there is loss. And so it does not have all the information in signal, yet it can be transmitted on a channel of much less signal capacity or bandwidth, say. And so that said, then with regards to signal and information theory, then it has the formal methods of like how much information can be conveyed. And so that's also as with respect to things like codes and the ergodic with regards to compression and decompression, with regards to lossy and lossless of signals, that then this sampling and information theory is very much part of any system that collects or transmits data. As with regards to data points and with regards to sensors, otherwise indicating things like in anything from switches to the measurement via any kind of interface or adapter of these things. So that's just kind of an outline of what gets involved when we're talking about things like data and plain tabular data or relational data, rows and columns of values, that then you can kind of think of waveform audio as just like a sequence of values with it as a tuple of different frequencies, but then how those are actually formed is as of from analog to digital conversion, and then as so related from digital to analog conversion of the forms of these values that are then just films or data. Again, data is kind of ubiquitous. Anything that has information. And for signal, the other idea with regards to signal that should be known about is signal and noise. So the idea is that for a given channel, it will have a certain particular maximum signal that can arrive via it. And so anything less than that is either absence of signal or it's noise. That this gets into when there's the noisy data or noisy signal, then noise is considered absence of information, absence of data. And so the idea between signal and noise is kind of like, it reminds one of the Sound and Fury or something like that. But the signal and noise have that then, it's possible to then figure out for what makes the signal is that most of the compression and what makes it possible to afford having something like video over the very limited as it might be bandwidth of a computing device or a digital transmission device. Has that what gets involved is compression. So already this waveform being quantized and sampled is compression of sorts of the analog data to the digital. That from going from analog to digital is automatically kind of compressive, and then there's going to be considered Shannon and Nyquist's theorem about how it's possible to have enough to guarantee that whatever his signal would be of a given particular frequency, that it can be perfectly reconstructed. That's the whole idea of Shannon and Nyquist. And then the rest of the signal in information theory is how can we squeeze this signal into this capacity and have it result that it sounds and looks like the signal on the other side. And then that gets involved not just mathematical transforms that are able to make relations of the data that is proximal, or as regards to any way to extract from just the big raster or pixel elements of the array, the matrix of these things, what would be a function that draws this same thing. Is that the most usual approach is that in the continuous tone imagery, which is different from like graphical imagery with sharp boundaries between things like text on a page. But for pictures and photos in natural and continuous tone imagery, then it's just usually related according to the proximity of things, and if they're the same, to establish kind of what are the boundaries and these kinds of things, and to only encode those informational elements. So that's another aspect of what gets lost in the analog, yet can still be retained in the digital, and then when it's converted back to analog can be reconstructed in this sense to be like so. Then other things that get involved with that are according to the color space and the models of vision, the models of perception that has studied various people and figured out what they can hear, in what ranges and registers of sounds that it reaches their eardrums and thus their auditory nerves and to be heard, or via what colors and stimulations of light and emission that in the intromissive of the eye to the optical nerves can be seen and sensed in this way. That the perceptual is studied very much, so that in the most usual and ubiquitous formats with regards to like A law and mu law in audio and with regards to JPEG and that's the frames of MPEG or all the pictures and video on the internet. A law and mu law as with regards to and PCM or for pulse code modulation or what. I mean various formats. That some of the most usual formats then have certain empirical perceptual knowledge encoded in the algorithm about what can be discarded, that's what's lossy, and then as with regards to what's reproduced and what's reconstructed and what's lossless is and that the idea that lossless is like that the lossy equals zero. And yet at the same time, that's the much greater cost of not being able to compress anything. So without losing some of the data. So these have been approaches out of signal and information theory for what it is, and then that's in with regards to why it's good to know these things, because if one were to try to take a modern kind of high definition television or even standard definition television signal and try to write that out on paper, say, it's kind of so that much like they said, oh, in the 1980s a wristwatch has got more computer than the Apollo capsule, which went all the way to the moon. is that like if I wanted to watch a video and it didn't have all these things built into it with regards to why it is so, that I would need a stack of intermediate elements miles and miles and miles long. So and I say that for me, but it goes for anybody. So the next time, observe somebody just kind of like casually like sending a video or even making a phone call, or as opposed to something like a text, like a simple message service text, which is just like it's 40 or 50 bytes. This is like a gigabyte, or like for Mula and Ayla audio and digital telephony. That it's amazing the embarrassment of computing resources that people don't know they have, don't know they're using. It's just kind of it's a thing. It's a thing. So that's about signal and information theory, I suppose. And with the Shannon and Nyquist are mentioned. So Claude Shannon and this fellow named Nyquist both kind of independently discovered this theorem that if you have a signal and it looks just kind of like a curve, a classical function, say, then if you sample it at twice what its fundamental frequency is, or it's the most frequency that it has, then it can result something that's indistinguishable from it. So this is called the Shannon-Nyquist, the reconstruction theorem. And then as with regards here to the real numbers, then it also is kind of related to the signal reals. There's three models of continuous domains. The complete ordered field, which is the standard that everybody learns in all the regular standard linear curriculum, the complete ordered field, as after wire stress. And then the line reals, which is like it's clock arithmetic. So if that's rational arithmetic, this is clock arithmetic. It ranges between 0 and 1. It is constant monotone, strictly increasing from 0 to 1. That's the line reals. And then the signal reals are kind of like, well, imagine we have the rationals or something else that's in a bounded region. It's dense, but it's not continuous. How can we possibly reconstruct that? It's like, well, that's what continuity is for. Continuity reduces this dense yet discrete, yet infinitely precise, all the data points by a signal that's continuous. It's basically twice as much. So then the halving and doubling spaces are associated with the line reals and the signal reals, these models of continuous domains that are objects of this domain of discourse, which includes a universe of mathematical objects in itself. So. Now it's hard to find that all in one place, the line reals, field reals, and signal reals. But it's very usual to find it all over the place with the line integral, the rest of analysis, and signal theory. All right, let's take a look here at what books we have. So we were reading from Lincoln Barnett, and we were reading from Einstein's Introduction, Lincoln Barnett. And then we got here this Hertog on I was going to look at that a bit and see what he has to say about what Stephen Hawking was getting up to, is with regards to the theories, the various theories of Stephen Hawking, and why they do or don't really have too much to care. Besides that, he was a great popularizer, and I learned a lot from Stephen Hawking's book, A Brief History of Time, about the light cone, and that there are no closed time-like curves. That's about it. That otherwise, though, the ideas about information theory, what it is, when there's the asymptotics and the singularities, is that here it's a continuum mechanics, and singularities are just openings and perestroikas, not catastrophes, but catastrophes in multiplicity theory. So that's then what we're going to take a look at here. So this was the numerical analysis. This is a book on programming. They have a new language called Kotlin. It's like Java. It's just some syntactic sugar on Java and simplifies things while still using under the hood all that's the engineering inside of the language of Java, say. And then I imagine take a look at this Hertog on the origin of time. And I think it was from about 10 years ago, and it's a bestseller, so it's a popularization largely, because it's kind of like they say, every time you add a formula to a book for popular press, half the people will quit reading. So this is copyright 2023, so it is pretty new. So we'll be taking a look at that then. Then we have here Boyer's A History of Mathematics. Now, I haven't read this yet, and so I'm looking forward to reading it because I read his conceptual development of the calculus, and it's great. And then there's the history of the rainbow, and it's wonderful, and it's great. And then so this history of mathematics, I'll be curious to kind of see what his lens has of the view of these schools of these men that make up these things. Thomas Hertog on the origin of time, or the origin of time. Stephen Hawking's final theory. A fascinating tour of cosmology, the universe and its origins. So there are at least two models of the origins of the universe. One is the Big Bang theory, and this is very much aligned with the usual theory from Genesis 1, that there was nothing and then there was the universe. And so when Lemaitre and Hubble and the Sky Survey and relativity and in the 1920s came together and found redshift expansion, then it made a perfectly suited case for the Big Bang theory, and that's been the course for 100 years. And it's kind of part of the idea of origins before. Is like, well, is there a Big Bang theory or was it always eternal? So then the flip side of this theory is called the steady state theory, and so then it's usually attributed to Bode and Hoyle in 30 or 40 years after that. And they said, hey, well, what if it's not Big Bang theory, but it's just always been around? Then it's like, well, then it's not Big Bang theory, that's the steady state theory. It's eternal. And for that, I think of something like Aristotle, and he's like, the circular mover is eternal. And then there's 10 or 20 years after that, then Penrose and Hawking were very much worked together and are known for their works together. But then what Penrose came up with is a cyclic cosmology. And it's like, well, what if there was a Big Bang? Did it end from a previous Big Bang? And does it just kind of go in cycles? So there's Big Bang, steady state, and cyclic cosmology is the idea of these kind of two theories of the origin of the universe, Big Bang and steady state, and then cyclic cosmology is kind of like, well, what if Big Bang goes around? And then the idea of that is, with the expanding universe, the Big Bang was that the universe would eventually end, if that's how it began, that it would end in heat death, cold death, or the Big Crunch. And then there's another idea that it could just not end. And so then that kind of gets into the whole idea what's cosmology is studying the sky survey. It's astronomy, and then trying to figure out, well, what does it mean for the whole cosmos of these things? And so there's Big Bang theory, steady state theory, and then there's these have various ways to arrive at, well, then what happens after that, and then there's that the idea has that for a long time the Sky Survey had that according to redshift, meaning like by Doppler, by light, and that's the only thing it kind of had. These are optical astronomy, radio astronomy, these days gravitational wave astronomy, that everything was receding and falling away. So the idea was extrapolated to like it started at a point, and then that's the way it is. That's the only way to look at these things. So then, with regards to the Big Bang Theory, it was held up quite well, and all this stuff about the inflationary epoch and expansion of the universe were tuned to it on average. Then, 20 or 30 years ago, stuff started coming up that has this, well, it's not like kind of so, because we got the galaxies hold together too well, so that's dark matter. There's more than the luminous matter that we can find and see, so something's holding these galaxies together. Here this framed is that just they're free and they're rotating frames, so they're just not falling apart. And then the other idea was dark energy is like, well, something is kind of boosting this redshift. I mean, these things are falling away faster than we could possibly imagine they were doing, unless they would have something pushing them, and there's no free lunch. This is impossible. And so then the idea is, well, then that's called dark energy. Dark energy is this other kind of missing explanation that falsifies the otherwise premier theory of the day. So the premier theories of the day, according to the Sky Survey and astronomy and the models and the configuration energy experiment, were wrong. And it was reached at some point in time. It's like, well, for sure we've got it so that it's past 5 or 6 sigmas, so standard deviations, that there is dark matter. It must be something else than what we have to explain things. And then it's so that it is beyond this for the dark energy. So basically the theory was falsified, and statistical hypotheses holding together were invalidated. So that's kind of tough to reconcile with these things otherwise. So then, about 20 or 30 years ago, they started coming up. It's like, well, first of all, let's measure the curvature of the universe and see if there's kind of a gradient to help explain why it's going along. And so WMAP or whatever, the background radiation, was looking for anisotropy, and they didn't find any. So it's like, well, dang, the universe isn't curved, it's flat. So that kind of throws away all these kinds of different kinds of explanations, trying to be candidates of what this explanation is, that to explain dark matter and explain dark energy, because for what they are, then whatever explains that fills for what they are, what dark matter is and dark energy is. That here dark matter is just, it's part of regular luminous matter, and how it is it's just part of this space contraction rotational, and because of classical mechanics is how it's arrived at in these more extended discussions. So it's established that the universe is flat, and that and it's not lumpy. Some of the modern accounts today is like, well, what if we kind of forget it's flat and then look at all the lumps? There's all these kind of ways, and so every day or week or so, some new article come up is like, somebody's figured out a new theory, and the idea is it's got to be like one theory is the idea, and so thusly. Then 20 or 30 years ago, then there was a study of the Sky Survey, and they kind of got up above what had been kind of like the usual way of looking at things. And they're like, yeah, how when we look at things, what does it look like? It's like, well, it's 99% redshift and then 1% blue shift. I mean, there is it's not like everything is falling away. It's just like pretty much everything is falling away. And so then, well, we got up and looked some more, and now what does it say? It's like, well, it's 51%, 49. It looks like, according to this later survey, it's like objects in the sky are pretty much as if they were floating around. Okay, they're just as if they were random, and without being as if expanding from a point. So this does not line up, of course, with the expansion account and the inflationary account and the Big Bang Theory. And what does it say for steady state theory? It doesn't say anything. Because neither the Big Bang Theory nor the steady state theory are falsifiable at all. Data can be tuned to that explains for it why it would kind of look like it were so, if it were so. But neither the Big Bang Theory, infinitely long ago, vis-a-vis, 13.6 billion years ago, nor the steady state theory like so. And so it's found that like most of the stuff we thought was close and fallen away as part of just our local supercluster. Our visible universe has grown. And besides that, our techniques are different. And so now we still look at the sky with these other techniques and it still looks like redshift. But we know from this also that it's half and half, not 99 and 1. So then that gets into the explanation for dark energy is like, well, what we're seeing is redshift bias. Because as light arrives, then it follows the geodesy and it's super classical, so it comes in out the rotating frames and is from the more distant, as having kind of added this effect of it having traveled around, so it looks like it's falling away. So that can help for explaining dark matter as part of luminous matter because it's just a classical free disk, and explaining dark energy as well, it's just an effect from the measurement. It's a redshift bias. And so what we do is we just can figure out ways to remove this redshift bias, and voila, all of a sudden it looks like, the universe is much more of an egalitarian place, as it were, in terms of the relative velocities of these objects in the sky. And so all of a sudden, and later experiments like James Webb Space Telescope and hopefully the soon Nancy Roman Observatory and other experiments are all lining up to say, oh, well, I'll be dang, we have just paint canned to be round filed almost all of inflationary theory. And now, and then how that's supposed to get to explain the crisis in cosmology as with regards to dark matter and dark energy. Here it's like so. It's like here's like, well, there's not really a problem once you figure it out. It's still so that like the universe is flat and the laws are, as far as anything can tell, the same everywhere. But there are extreme dynamics in the amazing heavens of all the things. The question of the origin hides the origin of the question is the quote that starts this thing. He talks about meeting Hawking, this guy who's writing this preface here. Hawking said, philosophy is dead. It's like, it reminds me of Nietzsche, when Nietzsche, Britain, universe or multiverse? A multiverse is a non-scientific proposition. You can imagine dynamics that establish superposition of states and that resolve to a thing, but they do, and so that's still a universe. See, it's a super classical universe with superposition of states according to extended bodies vis-a-vis the point like and how we think of things as particles and in the classical, but it's not the same thing as universe. Multiverse, rather. So it's talking about Hartle and Hawking and Hertog here. Talking about the late 90s. It were the culmination of a golden decade of discovery in cosmology. They had tuned inflationary theory very much so. And now now that's not so. That's not so anymore. So he talks about the expansion history as it is. We live in a supercluster, the LaniaKea, the Garden of Heaven. And what that means is like, well, even if it wasn't a Big Bang, the whole universe, at some point in time there was like a cosmic filament or something like that. And that exploded. So we're part of what's called a jet. That's the old visible universe was discovered to just be a jet, And so that also explains in the closer things that are falling away, that there's still, that's explained also furthermore by this as the way it is. He ran the evolution of the universe backward in time at the same rate. He found that the galaxies must have all been in the same place at a given particular time. And he gets into reasons why they're thinking about, like, well, when was expansion like so, and when was it like so, and why was it like so, and when was it like so? And then all these different factors are given to be like, well, how would that be so to, like, give what we observe according to spectroscopy the distribution of the elements? It's like, whatever works, and so that's what they have, kind of a thing. Vis-a-vis not being able to say anything about the laws of physics as they are today, nor anything about the laws of physics that they're all the same everywhere, that they would ever be any different. So he talks about the scientific revolution, and Ptolemy and the Almagest was as much geocentric as it was anthropocentric. Miletus and Anaximander from Miletus. Plato, like in the world of our experiences, and he's talking about this classic kind of derivation, mathematical formulation of nature's laws that embodies what physicists today mean when they use the word theory. Physical theories derive their utility and predictive power from the fact that they describe the real world in terms of abstract mathematical equations that one can manipulate in order to predict what will happen without actually observing or performing the experiments. And it either does or doesn't. In a stricter philosophy of science and statistics, theories don't predict. They just aren't invalidated. And then over time, that can bring a particular amount of certainty, or something along the lines of confidence. It can bring confidence, but just confidence that it's not wrong. The confidence that it's right is false bravado, say. So when I see loose language like this, I kind of think it's like that's unscientific, and it can be an insult, to somebody if they say they're a scientist. Crucially, the discovery of the Big Bang means this isn't just a philosophical question. In fact, if the Big Bang is truly the origin of time, then it would seem that Poincaré had better be right. For if the physical laws are to determine how the universe started, one would have thought they must have some sort of existence beyond time. Here it's usually considered that the beginning was infinity ago. So, while Poincaré's vision is interesting and important, we're talking about Poincaré. Here he says, to the early 20th century French polymath Henri Poincaré, the notion of unconditional platonic laws was an indispensable presupposition to do science at all. Then he says, the theory confronts us with some of our presuppositions on what physical laws are ultimately about. And yeah, they do. So, it's wrong. These platonic leanings on matter, well, not obviously wrong, differ radically from how, ever since Darwin, biologists came to see design in the living world. And then we get into emergence and stuff like that, but and Darwin is like the sum of histories without the sum of potentials, because the sum of histories and sum of potentials here comprise to make a pretty thorough thing. They act over long periods of time. So and that is the law here, vis-a-vis just like, induction. Again, this is the problem of only having kind of like a half inference account. That's linear induction is not ever wrong, because it is, and it is in the infinite. And so we have deductive analysis to help provide the fuller dialectic of these things. And so the author here has kind of he's got a classical theory, but it's a super classical world. And ever since Duns Scotus, the infinity is in, and it's super and it's natural, supernatural. So he's talking about theory, Darwinism. Oh, string theorists. So he's talking about this golden years, which was like when everything was still right before all this, data started coming in, casting it all quite into question. The unexpected observational discovery that the universe was accelerating is not so. Tied in with equally surprising theoretical developments that suggested that the laws of physics might not be carved in stone after all. Also not so. So these scientists and physicists, they're being rational. But their data was bad. Bad data it results in what computer program is called GIGO, garbage in, garbage out. So that's something to figure out. Soon, string theorists began to envisage a variegated multiverse. Here, string theory is just part of continuum mechanics, and so it's a universe of string theory. String theory is just twice as much smaller than atoms as atoms are than us. It's just part of this sampling and reconstruction, as if with Shannon and Nyquist, to have it so that it can still have the methods of discrete mathematics that works on these elements way up above and treating them as continuous things. So it's just kind of a conceit to a greater continuum mechanics and what that needs. So this string theory arriving at multiverse theory is that quantum mechanics already arrived long ago at multiverse theory, because they have a model of particle mechanics that's non-deterministic and probabilistic. It could be anything. And so then this and that and the other, and then just saying, well, we got all these pocket universes, and there could be anything in them. It's like, well, you can have very highly dynamic regions of arbitrarily unbounded yet still finely bounded amounts of space and space-time, where there's a gradient of this or that or the other, some lump or clump or whatever you found in the cluster in the Crab Nebula or something like this. But that doesn't change all this other stuff otherwise. So anyways, that's just saying that this account of string theory is not necessarily accurate, because there's one account of string theory that's continuum mechanics. Then he talks about Kepler, and I really enjoy Kepler. Kepler came up with a model of solar system based on this ancient platonic solids in a metaphor and some relations after like Bode's law, B-O-D, Bode's law, which is close. And he's hypothesizing to reconcile the ancient platonic dream of the harmony of the spheres with the 16th century's insight that the planets move around the sun. And so Hertog says it would be futile to follow in Kepler's footsteps and search for a deeper explanation of the fine-tunings that engender life. And it's like the physical laws, life. There's life in the universe regardless of the physical laws. That's the usual notion of like an animism at all, as with regards to like carbon-based life forms of the biological sort, and who want their coffee and their paper every morning. That's not so necessary here. And as with regards to Darwinism and the origin of species and stuff like that, or the origins, of the anthropocentric in the universe. These are people who don't really. I wouldn't say it has a very firm ontological commitment. It isn't a profound mathematical truth that renders the universe bio-friendly, they hold, but simply excellent local cosmic weather. Any impression of a grand cosmic design is an illusion. So here it's just like, it's it's just kind of a given, and so the laws of physics have never changed is the idea. And then as with regards to why we evolved like eyeballs that deal with the optic, is because the optic is just light is special and it's perfect in a sense. Because then after the space-time continuum and then the dimensions of the resources, the numerical resources that make up this kind of thing, they have that it can be quite perfectly natural. And then with regards to biology, and that usually refers to like biological reproduction, as with regards to eukaryotes and gametes and stuff like that. I mean, later for higher organisms of a sort, and that have genetic evolution, as with regards to the biological mixing of genes vis-a-vis the clones or just this kind of thing. So with regards to the random combinations that arrive that make for the usual model of survival of the fittest as fair as simply as tendencies and propensities, and what makes for minima and maxima and these kinds of things. Emergence then, I'm definitely saying that from reading Hertog's account of quite a large swath of science's account of the laws of the universe and trying to figure them out, I'm looking at it seems to me a very fragmented picture of non-explanations compared to that well, there's at least one, and then all these experiments that went in to kind of give data that had given the wrong idea that is not so, or because their theories were eventually inconsistent, so then they just added whatever. Not so. Has that here it's like that doesn't have to be so either. He says multiversists, however, don't give up easily. The multiverse is a great idea for the fourth dimension, and the idea that there's anybody has got their own perspective on things, and that's their own objectivity and then for the intersubjective. But multiverse in a universe all lives in the universe. Universe wins is kind of the idea. But otherwise, multiversists or SRians are not having a very full theory, I'd say. And then they talk about the anthropic principle. These are like, well, if I'm not going to have my objectivism, then I'm going to be the center of the universe. And it's like, well, you're welcome to have a theory where you're in the center of the universe. In fact, most people do. It's not physics or science. And then philosophy says no, is what I'm saying. He talks about Steven Weinberg. Now, I would separate Steven Weinberg from Hertog, because Weinberg is one of my favorite physicists and scientists today. He's talking about Weinberg and talking about Higgs theory. Most advances in the history of science have been marked by discoveries about nature. But at certain turning points, we have made discoveries about science itself and what we consider to be an acceptable theory. We may be at such a turning point the multiverse legitimates anthropic reasoning as new basis for physical theories. Well, now I disagree with that. Physicists say the multiverse saddles us with a paradox. See, paradoxes are problems. Paradoxes means the theory is wrong. Multiverse cosmology builds on cosmic inflation, which has been roundly paint-canned and deserves the round file, which is a euphemism for the trash can. Inflationary theory has had a wealth of observational support. Dust in the wind. So yeah, that helps. That does help establish kind of like the what and wherewithal, but then what it gives is like it's just like this is the last few decades of data has kind of refuted this. So I'm gonna read this. I'm gonna read this more thoroughly and some more, but not much more. Have a great day, gentle readers. Tempus fugit, carpe diem. Time flies, seize the day.